Okay, I have it. Okay, so let's talk a bit about composition space modeling, neutron reflectometry. Yes, Thomas, you said we've been doing that for quite a while, and I will even go a little bit further back than what we've been doing. Um, so composition space modeling was what is that? Basically, what that means is that the primary place where you do your modeling, where you construct your model, where you construct your structure, is the compositional space or real space. Meaning, I will be talking a lot about lipid bilayers. So you see one here, but that's also applicable to other soft matter interfaces. So what that means is, let's say in terms of a lipid bilayer, that what we are actually modeling is the distribution of the molecules and molecular groups across the interface, meaning across the surface normal, rather than modeling in scattering length density profile terms. So that is what composition space modeling means. This is advantageous in many of the biological and also some of the soft matter applications, because then you can use information that you actually have about your system, like chemical connectivities, identities, volumes, immediately in your modeling process. So you have much more information or much more assumptions that you can use at the beginning of your modeling, which on the other hand also means, of course, that you need to know already more about your structure to use composition space modeling. So if you're not certain that let's say here you have a little bit bilayer that you want to model, then you shouldn't use such a more constrained model and go back to other models. So then after you basically constructed your model in real space, then typically this canvas here is microsliced, transformed into a scattering length density profile, and then from that reflectivity is calculated, and this entire thing then forms a traditional data analysis loop that's iterative loop that's known from other modeling as well. Okay, so this is composition space. Typically, when you do composition space modeling, your canvas here on the right and white is embedded typically in slabs, so that you don't have to model your entire interface just with a composition space model, so you avoid micro slicing over very large distances. And that's something we also do. Listed down here is a review that we wrote a while ago if you want to read about that particular part. Doing a little bit of history about composition space modeling, that's quite interesting. So I think the first time that I saw composition space modeling being done is in a publication here in 1982. Well, I haven't seen it at the time, but here at this particular graph at the beginning, where there's a volume fraction versus a distance, you see spatially overlapping groups. This again is a lipid bilayer, so you have the polar groups and let me read it, cholesterol parts of why is it called cholesterol? It's so old, even the naming is different there. But you see, have submolecular groups here that overlap that were modeled like this. It is works by Franks. And this already qualifies as composition space modeling. Then more relevant for and more influential for the things we've been doing than work by Wiener and White in the 90s. What this group of around Stephen White has done is first partitioning molecules, particularly lipid molecules that we use a lot, the same way we still do today in parts of the hydrocarbon tails, with or without methyl groups being separately, and the phosphocholine head groups, dividing them in particular parts. And those were done based on scattering length densities for neutrons, but also electron densities for X-rays, because in the end, much of that early composition space modeling was actually initiated to do a simultaneous analysis of X-ray and neutron scattering data, because people saw that using SLAB models for this particular application was not quite ideal, because the electron density and the neutron scattering density profiles had a significantly different shape. So that's why composition space modeling was developed. Also, what Wiener and White introduced, which was actually sort of a hindrance then for later composition space development, is introducing the notion that submolecular groups should be described by Gaussian functions. So they made that popular, and people stuck with that quite a while, but that was actually a problem, as I will show later. And then just the third highlight here, this is work from the Nagel group. I listed that mostly because of how impactful their work has been using composition space modeling. So this is their SDP model here, developed by Norbert Kucharka, in which they did a lot of diffraction work on lipid bilayers. And most of what we know, or much of what we know about lipid bilayer structure, came from that group and composition space modeling. And yeah, actually the term composition space modeling, I believe, was termed by Stephen White in this in those papers referenced down here, but they might have taken it from somewhere. I'm not 100% sure. Okay, and contemporary work in composition space modeling, it's not as widely used as you would say. There is here, this is the soft matter, my soft matter example. This is a soft matter work from Emanuel Schneck's group, where they describe well, there is a lipid bilayer interface, and then polymers, they use composition space modeling in a sense that indeed the modeling takes place here in real space, and then a scattering density profile is calculated. There's also related work, very good work coming out of ISIS, and this central reference here is also, I think, related to ISIS in some respect, where the modeling still takes place in scattering length density space. So you first obtain a SLD profile, but then you derive from that profile the real space profiles, the composition space or volume filling profiles, in a way that even here in this right column, work from Stephen Hall and Luke Clifton is involved, you actually get even uncertainties that on your real space models, and you have protein here that span the lipid bilayer. So the end result is comparable to what I introduced before in terms of composition space modeling. The only drawback is that if the system becomes very much complicated, going this route becomes more and more difficult than modeling the composition space up front, the real space up front, and going backwards to the scattering density profile and the reflectivity. But otherwise, those approaches are equivalent. Okay, so what have we contributed to the entire thing? We started back, this is our original publication, 2011, which contains many of the original ideas. And the first thing we did is, as I mentioned before, we got rid of the Gaussian profiles, Gaussian functions to describe single molecular groups. And we went to a function that can actually be much nicer combined to build up structure. So the problem with if you have two Gaussian functions, two Gaussian profiles, let's say here a blue one and a right one, those are not Gaussians, and if you want to then join them together and really move them close, and you have a structure like a lipid bilayer that fills the volume 100%, so no overfilling, no underfilling, then this is not possible with two Gaussian functions. Because if you move them, let's say, to this half-height point, so that they really touch each other at this half-height point, the Gaussian function is not symmetrical. So there will be either over or underfilling. So if you choose a functional form for your single molecular, for your basic building block of your composition space model, you should use a function that is symmetric around its half-height. and there are plenty of functions out there. We, in the end, used pairs of error functions for the reason that if here on the left side you have a head group. So this is the actually a phosphate part of the phosphorylcholine head group. You have a number of 5 atoms in here. They span a certain space. So there is a length associated with that. And the Gaussian function assumption was that basically if you have thermal broadening or conformational broadening, this would be best represented by a Gaussian function for a single atom. So we should also describe a molecular group by a single atom. So taking this assumption might or might not be true. It's not that easy, but if you actually have a spatially extended group and you assume that this has more or less a constant area, well, area per group or cross-sectional area, then this would be such a box here. And then if you now take that box and actually convolute it with a Gaussian function, you will get a pair of error function. So this is what our motivation for error function is. But in the end, given our resolution and all these assumptions that go into that, it doesn't make a big difference. You could have chosen any other symmetrical function. Do you actually see my mouse when I move over
that? Yes.
Okay, that is good because I would not know how to turn it on in Keynote here. Okay, so we have pairs of error functions that give nice distribution as shown here, which now you can use to build up bigger structures and which intrinsically fill the volume that you have. So we've shown then how to do this in this paper. So it works indeed. Let's say for this bilayer structure here, which is a tethered bilayer structure. So you see the two big hydrocarbon chains in red, the methyls here in black. The head groups, I think they're lumped together into one distribution in blue, and then you have a bunch of groups for our tether structure. And you see, indeed, those groups here nicely fill the volumes here in the center of that lipid bilayer. It is 100%, not more, not less. So, and this is simply because you have chosen the correct functional form. If you then want to build up a bilayer out of those groups, you have to do some accounting. So this is, we came up with a scheme how to do this. This scheme is published in the supplemental information if ever anybody wants to read it. It's also integrated in our software library, which I will talk about. And it basically takes into account once you have once you have constructed your bilayer with, or let's say a single molecular group, as in terms of a unit volume, so one group, or you have one group that you want to place now here on such a canvas. Actually, how much of that group path you have is being modified by the overall surface coverage of that group, by the actual volume of that group, by the stoichiometry related, let's say one head group to one tail, that's a one-to-one stoichiometry, but also by other modifications, like if you have, let's say, an outer leaflet and an inner leaflet here, and the area per leaflet is different, then suddenly you don't have one tail in the outer group and the outer leaflet for one tail in the inner leaflet. So there are all those relationships which you need to track. And we have a scheme how to do that, which is listed here. So it's doable, and then you can build your group. So we've done that for bilayers. As I said, I work with bilayers a lot. If you have other basic units like a bilayer, you would need to do that yourself, and then use that as a module in your software or whatever. We have validated that model, composition space model, using those error functions against MD simulations. So back in the time, we did an MD simulation, actually several MD simulations. This one is one of a DMPC bilayer at a relatively low hydration in terms of water molecules per lipids, but that's not the point. So it's not a very biomimetic example we've chosen, but it is a lipid bilayer, has been simulated, and we can show that the model can find values for the parameter values for the groups that describes those distributions very well. So this is the left side. But on the right side, then, if you actually look at first, if you just take from the simulation, so those are those traces that you see here, the mean positions of every atom, and then the standard deviation of every atom in a lipid bilayer, you see they vary quite a lot. So the mean positions, well, they follow more or less your lipid molecules, having the methyls here close to the bilayer and the choline atoms of the choline part of the head group further out. But already looking at the standard deviation indicating the flexibility, there's quite some difference here, which for the two chains, of course, they stem from how they are connected here to that glycerol group. But you see you have a large mobility around the methyls, even for DNPC. You have a large mobility around choline groups, and now you're trying to model that with a one-dimensional composition space model. And it does the job, but it takes some shortcuts. Well, shortcuts. It needs to adjust to that. So if you now look at those crosses indicate the actual interfacial roughnesses, which should correspond to the standard deviation of those atoms at those positions, that it is approximately right. So they follow the trend. But of course, they don't really 100% correspond to what you see here. Also, if you see where the boundaries of those groups were set by the model, that they mostly agree. If you compare that to those mean positions, but particularly here in the head groups, you can really see that, well, sure. So this O of, for example, here from the phosphate group, that technically resides in the choline part. So you see the composition space model does a good job of describing those curves very well, but you shouldn't look too closely, or you should acknowledge that it's still a one-dimensional representation of, in the end, a two or three-dimensional object that you're trying to reconstruct, and there are limitations to that. If you want to know more about this is also early work, well, 2001, yeah, quite early, from Erich Polish, who actually looked at that and was quite revolutionary for its time, looked at modeling and constructed a 2D and 3D models of molecules, which then I think he adjusted in a Monte Carlo way to fit X-ray and neutron data in a way. And this really goes more deeper in what we're actually trying to achieve with one-dimensional modeling and how feasible that is, and what potential next steps are, I mean, short of running an MD simulation for every data set that you measure. So if you're interested in that and the limitations of modeling, that's and other things, that's quite interesting work to follow up. Okay. But so we're happy with our bilayer implementation. We also know now how we can build those compact objects in composition space modeling. The next step then, what you want to do often is take one of those modules, take one of those objects like a bilayer and add something to it. So for us, adding something to that is usually protein. So we can take a protein here. You see that now in red. So the bilayer is on the left. Those are the pairs of error functions. The protein you would now have in red. The protein now often is being modeled differently, either freeform like and as a hermite or other type of spline. And then you can also incorporate that into your composition space. And we do this two things are kind of note here. First, proton exchange. It's also important for some lipids, but very important for proteins. So you need to take care of that. You need to know how many protons you have. You need to know what is your bulk solvent, and then you need to do those corrections. And also, once you move your protein into your lipid bilayer, you have to take care of replacement here. So now you're in a situation where you don't have two groups, and you just need to move them close to each other because you know where one ends, the next one starts, but now you actually have chemical overlap. And in a more general thing, this is done in two different ways. So each of those objects, now we have to talk a little bit about implementation here. Each of those objects, has the ability to draw themselves on the canvas. And there are different methods how this is being done. So one mode is, in terms of modeling, is just the addition method, where if you have two things like a blue and a red square in this case, so you want to draw them both on the canvas. That could be the bilayer, this could be the protein or anything else. You can just have the addition method, meaning first you draw the blue square, then you draw the red one, and the red one just adds. Wherever you draw that, it adds to that. If I would have drawn it here to the left, I mean, half of the red square would have, like in a Tetris, have sunk into the baseline here. And what this adding does, it increases your maximum volume or your unit cross-sectional area of your canvas. And this is one method that you can use at the beginning or at a certain stage or any stage. And then the other method is the replacement method. Let's say adding protein to your bilayer. And what you do then is the unit area or the volume typically is fixed. Your bilayer might or might not fill the entire available volume. If you then add protein, it is partially added onto it, and the other part replaces the existing core. So how this is then done typically is that this amount of replaced volume and where it is replaced is reported back to the blue object, in our case, let's say the bilayer, so that the blue object, the bilayer, can update its state based on that. So you want to know, did you replace head groups? Did you replace tails? How does this affect the stoichiometry? So there is this feedback. So those things can be quite difficult if you really want to come up with a general way of how to model that. Our canvas is not smart, meaning our canvas that we use, once you paint something onto that, it actually forgets what you painted on it. You just have a volume and you have associated scattering. So this reporting back is done in a way that is sufficient for our needs. It does the job, but it is not within an implementation that is where each object is fully aware of the surrounding objects and so on. So this could be done. We can go there once we need to go there. But at the moment, we just know we replaced this much of that part of the bilayer. We give only those numbers back, the bilayer, which we calculate itself, and be done. Okay, so once we have this in place, once we can do this kind of modeling, adding proteins, then we use that quite a lot. And the first next thing that we wanted to do, this is now, where are we? 2017 now. We wanted to model protein complexes, where one part of the protein spline that you add is deuterated, the other one is proteated. And you can do that first by having, again, your bilayer object, having your protein object, again, a spline, and you just add another parameter to your spline that the scattering length density, which previously was fixed, is now actually a fittable parameter. So, and you can easily see now scattering density for your spline is here on the right. It's the black curve, the volume is the red curve. You see that there is a deuterated high scattering length density fraction here, the low scattering length density out here, and here it goes back up, but also there's very little material. So you can see that this peptide, which is a ligated version of a deuterated N-terminus and a proteated C-terminus, the N-terminus is sitting in the bilayer, the C-terminus is sitting out. So that was kind of the first implementation of how to now extend this composition space approach in terms of proteins to protein complexes by taking the scattering density into account. We're still doing it this way. We are just usually not showing it in this way. We just then would show the the different components of a complex or of a ligated protein like this in the following way. So this is now current unpublished work where we have the lipid bilayer, and then you just see those splines for those individual parts of the complex after we reprocessed the data. And so this is now a tertiary protein complex, which will require more than one measurement. So this is actually 3 measurements on the same system with different duration schemes, all put together in one fit. And then you can delineate those constituents of that 3 protein complex. What this then also enables, and I just have one slide on that, is integrative modeling. So integrative modeling is when you take other techniques, other information into your data analysis. In this case, often it is structures, high resolution structures of proteins from X-ray, from NMR data, and other techniques. So this is an example of a GRAS protein, where we take the available X-ray structure and also import it into our composition space model with all its residues. And now we have a rigid object that we can rotate, that we can move in and out of the membrane. And this is being handled the same way as a spline would be handled, just that it's a different kind of object. And you see in many cases that works very well if your X-ray structure or your NMR structure is still valid in your membrane context. The actual spline here are red, and the X-ray structure in this dotted line under the right orientation, they match up very well. And that's something we see quite often. Okay, just a few examples of what you can also still do with this composition space modeling and how far you can take it. So this is now just an example of neutron diffraction data. So it's a recent publication where we had a neutron diffraction data from a not that relevant lipid, but which give really good diffraction data. I think something like 13 orders of Bragg reflection peaks, where you then have really good spatial resolution, so that you can use a large number of molecular groups to fit that to describe that data. And that's what we've done here in this example, and you see it really nicely fills the volume, and it also fits the data very well. And this is also then a good test case to again look at those things I talked before, how realistic are actually, now that you have really high resolution data, how realistic are the parameters that you obtain in your 1D composition space model to the structure, for the structure that you're describing. And also here you see you very quickly approach those limitations I was talking about. You can also use this composition space model for sans fitting. So I've done that a little bit on the side, just because it seemed like not much work to do, and indeed it wasn't. So what we've done is taking from ZASView one of their multi-core shell models, where you're just now using those multi-cores as a micro-sliced canvas. And then you kind of paint your canvas onto those slices. And this is very good to describe vesicle structures. In our implementation, vesicles that are large enough so you don't have much difference between the areas here of the inner and the outer leaflet. So we use that, and then you just use ZASView, process this object, and you can now fit sans data with the same model, and it reproduces published data very well. So that's very nice. It can be done. It hasn't found a big reception in terms of use cases, people are not that interested in using that because there are other models for instance that do this kind of stuff, but it is available and it's an easy extension of what we've done. Okay, so this was kind of me talking about composition space modeling, how it's done. In terms of now practical, in terms of software, recently, I think 2 years ago, with big help, well, not just help, I mean, really, with David Hugerheide, also NIST colleague from here, we took that that library, which is, we call it mole groups, and was usually in C, was originally in C++, and we ported it to Python for better integration with Refl1D and for better integration with other fitting software, like the two examples I've just shown you before. So this is now available as a Python library. This is the repository that resides under the Reflectometry repository, where you also find Refl1D and other tools. And this mole groups library now contains a relatively large number of objects that can be used. Simple objects, well, like the two arrow functions. Simple objects like composite objects that they're just, which can just hold several other objects and form new objects, and then applications like various bilayer structures, protein objects in spline or discrete that can take in a PDB structure, and other objects like this. So you find that in the library. There's typically those objects are contained in this mol.py. Then we also have a small library of already predefined components and predefined lipids that are ready to use, so you don't have to put those simple molecules together yourself. And then there is a relatively large number of examples that you find there also. So for Refl1D, so for reflectometry, for diffraction, for SANS, and also for the previous GARREFL application, which is probably not relevant anymore. So those examples are in Jupyter notebooks, meaning that to use composition space modeling, our package it's still a lot of scripting, so it is easy for somebody who's familiar with those kind of things, but it's still quite a barrier for new users to start using that, and so that's something to note. Just give you a quick idea how that works. For example, if you want to, let's say, fit a bilayer with a neutron to your neutron data, what you can use, for example, you can, and some of those, as I said, are already predefined, but you can define components using the component library. Under the hood, it uses Paul Kienzle's periodic table library, so that you really just have to give a formula, a volume, and then it calculates scattering length densities itself. It knows the difference between H and D, so taking into account proton exchange is relatively easy. Then you can take those components, compose them into lipids in a relatively straightforward way, showing here for DMPC. So you take your tails, you take your head groups, you define what type of methyl you want to have, because there are different types of methyls, and then you have your lipid molecule. And then similarly, you can now combine your lipid molecules into a lipid bilayer. This is just a bilayer. Those are solid supported tethered bilayers. So there are different types of bilayers. You say what lipids you would like to use and at what fraction. It also supports asymmetric membranes. And then you have your bilayer object. And then within this script, this bilayer object is with Refl1D, you would take a canvas that is provided here, in this case by functional profile. You have your parameters, and now this this function, which is called bilayer, which you will have to define, and I'm not showing that here, will now take this bilayer object, will take the parameters, and make the bilayer object draw itself into the canvas by the rules you specified. And well, here in this case, in terms of Refl 1D, now this canvas is now embedded in just a stack of otherwise slabs. So this is the hybrid model. So this is kind of, you get an idea how you would deal with this on a script basis, straightforward. And what we're working on now, again, this is David Hugerheide again, and Brian Marin will, in the newest iteration, or soon to release Refl 1D version, which can be completely also used via a browser interface. There are now you have the possibility to have custom plots, and David Hugerheide worked on having one of those custom plots being the molecular model, your composition space model from mole groups. And this is an interactive plot. So once you have loaded your script into Refl 1D, you can interact with those parameters. You can check your model. You can see how it behaves. And that's a nice addition, and one of the steps we're taking to lower the barrier to actually use it. Although you can't use Refl 1D directly to put your model together just yet. Okay, and that was my last slide. With this, I want to thank people at NIST and Carnegie Mellon, and take your questions.